Good morning, everyone, and welcome once again to the JKMRC Friday Seminar Series. On behalf of the University of Queensland and the Sustainable Minerals Institute, we would like to acknowledge the traditional owners and custodians of the land on which we meet today. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connections with country, and we recognise their valuable contributions to Australian and global society. It's my great pleasure to welcome today Dr. Tuan Nguyen. Tuan is from the Centre for Mineland Rehabilitation and is a UQ Amplify Fellow at the SMI UQ with a background in chemical engineering. With over 15 years of research and teaching at UQ, he has been working in a diverse range of research projects with a primary focus on advancing fundamental knowledge and developing environmentally friendly and sustainable solutions for minerals, oil and gas processing and environmental pollution management. Tuan's current research is centered around reprocessing and redesigning mineral wastes for goods, which includes investigating non-conventional stabilisation and solidification technologies, carbon locking methods, and rare earth element biomining. The title of his talk today is Embracing Multidisciplinary Approaches to Mineral Waste Management, Tailings Dewatering, Geopolymerization, Upcycling, and Biomining. Please join me in welcoming Tuan.
Thank you. Good morning, everyone. Thank Christy for introduction. Thank Tom, Christy for organizing this, and I would like to thank you, Lisa, as well for connecting me to this opportunity to give a talk at JKMRC Friday Seminar Series. So the aim of my talk today is very much to try to emphasize the importance of adopting multidisciplinary approaches for mine waste management, and hopefully we have enough time. I have enough time to take you through 3 case studies that I did when I was at School of Chemical Engineering, as SMI, and sometimes as AIBN as well. So before we start, I acknowledge the traditional owner and their custodianship of the land on which we met today, and pay my respect to their ancestors and their descendants. So I would like to spend a couple of minutes to set a context for my talk. Hopefully we are talking at the same scale and same technical language. So very much this illustration has been around for a couple of years, and it's very much give us an impression of how big the tailing problem, the problem that we are solving. So globally, it's accumulate around 282 billion tons of tailings. That's including the water and the mineral waste and the water. So you can see that the amount of tailing can fit into that box with around 6 kilometers each side, cubic box. And that box is relative to the map of New York City underneath. And the contribution to the global tailings is different by different commodity. And you can see here, copper, a lot of tailing from copper, 46%, followed up by gold, iron, coal, 8%, that's a lot. And copper, less zinc, is also very important. So the mining future should focus not only on the technology advancements, but also on reducing its environmental impact, including minimizing its water, weight, and carbon footprint. So the waste management hierarchies introduced by ICMM very much give us the identify all the important tasks in a different rank that we need to do in order to have a tailing reductions. And if in this waste management hierarchy, the higher up on the higher rank is reversed. So we can see that from the plant upstreams, we have option to have reductions and prevention, which is very hard. From downstream option from the plant, we have reuse, recycle. And then we have recoveries. And the last option is, and not refers, is the storage option. The higher rank is refocable, but it does not necessarily lower rank have a lower difficulty in terms of technology. So I can see that all of these tasks, we have all degree of difficulty in terms of technology there. So this term of circular economy has been very common, and it's come to my surprise as well when I prepare for this talk. We have another term for low carbon economy, and we have another term for bioeconomies. And within that bioeconomies, we have the bio-based economies. So very much when you use biomaterial, this is part of the bio-based economy. And the intersection between those three very much is the sustainable economy. So my research on sustainable resources and environmental engineering, so aim to enlarge those boundaries of sustainable economy and have it become even larger. So today, I just try to positioning three of my talk within that three circle. So it's just somewhere around the circular economy, low carbon economy, and one in the bio-based economy as well. So we call it biomining, or under the umbrella of the biomining. So this is the first case study. So we talk about dewatering tailings and its sticky problem. But before we go to that first case study, I will go back to the Euro with the questions, how many disciplines are involved? So it would be great if you can help me counting how many disciplines involved during my talk. And then we will come back to this question at the end of my talk. So you may ask why we need to dewater a tailing. So this happened around the world. So up until now, just last year, we see 2 more tailing dam failures. It's happening, keep happening. So there are a need to come up with a better way for tailing management. And dewaterings and dry stacking is now no longer a trend, but a necessary in mining, in mine tailing management. So the demand for dewatering is very much proportional to the percentage, the contribution of that commodity on the global tailings volume. So we can see that there are a lot of need from the copper commodity, but also coal tailings with 8% also, and they also need dewatering, their tailing as well. So this is a case study. So driven by that trend. So this is quite interesting operations. So for example, this is one of the information extract from this paper. So very much this is a new, quite relatively new coal mine. And it's run around 2014, so around 10 years ago. And the statement is make it very clear, no tailing dam are planned to build inside or outside of mine lease boundary. And instead, their tailings will be dewatered by different dewatering devices. And then it will transfer to the dumping site by truck or by different equipment. And sometimes the dewatering tailing can be co-disposal with the core rejects as well. So this is very much the, when you try to dewater the tailings, this is the data, the moisture of the tailing after dewatering. So we can see that with the bell press filter, currently it's around 37–40% moisture content. So that's they read the limits. So basically, lower content is better, lower moisture content is better, but that's the lowest they can get. So around, they struggle around that 40, and they aim to reach 37% of moisture content. And then you will see that the moisture content is fluctuate a lot over the time. And that's a part of the problem is because of the clay or the fine, ultrafine particle inside the tailing. So 80% of the coal mining in Queensland are from open cut. And because if you look at the map of swelling clay, distribution of swelling clay and the non-swelling clay in the subsoil, we will see that when you move to the center, around this area, you will see that the clay is a big problem. So clay normally we divide into two different types, non-swelling and swelling clays. The non-swelling is the type of one layer. So one layer of octahedral and another layer of tetrahedral. So that's one layer clay is okay because the interaction force between the clay platelets is very strong, so water cannot absorb into it. But another type of clay is 2-1 layer clay. So we have octahedral layer sandwiched between the two layers of tetrahedral, and because the interaction between the two platelets is very weak, it's quite weak. So because that water can go between them, and it's trapped in there. So it's really hard to get rid of that kind of water, and because of that, the moisture content cannot go down further. So because of that, they have a coal mining. They want to investigate to see whether we have any other dewatering methods, or even if we can have any chemical support. Then we can come up with any chemical that can help to reduce water further. So this go back to this flow. The tailings come out from the flotation circuits. We go into the thickening state for the solid liquid separations. And this for the solid liquid separations, in the driving force for the separation is given by this equation. So very much M is the mass of the solid, mass of the particle, and A is the acceleration. So if it's in the thickening tank, the driving force for separation is very much based on gravity. So A is just equal to G, really very slow. And in order to shorten the time, polymer flocculation normally add into this tank. So when you add polymer flocculations, particle will aggregate together and M become bigger number. And when M become a bigger number, we have this, the driving force is stronger. So that's how I have to reduce the separation rate. However, it's still too long, and the moisture content after the thickening state is still very high. So the slurry come out from the thickening state. You go into different. We need to use different mechanical force to further dewatering. So there are a couple of options. The bell break filter, very common option, but in our solid small centrifuge also a very good option as well. So at the School of Chemical Engineering, we have a pilot scale of solid small centrifuge in there. So if you need to do any test with solid small centrifuge, just talk to us. So if you use the solid small centrifuge, for example, the driving force separation in now is the same equation, but now the acceleration is now given by this formula. And A now can be up to 3,000 Gs. So it's 3,000 times faster than just by gravity. So that's how it makes it faster. Another important thing is the thing that's coming into the solid small centrifuge, it come out from this tank. And normally we have chemical in here. And in line from here to here, we can inject some chemical as well. And we still don't know what is exactly what is the effect of chemical on the combination of M and Bro here. Bro is the density of the solid part. So the synergy between the chemical effect and the physical effect on the what the watering is still not very clear, not very fully understand. So today, our group, we did a lot of comparison between different devices and different chemical, but today very much is just bring you to one set of data, just to show you that in order to have that problem, we need to bring out another knowledge from another discipline. So we did it in a food engineering. So the problem here is because after the watering, we need to carry the cake by truck to the dumping site. And when you dump the watering tailing, shear strength is very important. Shear strength of the material is very important. So we need a higher yield stress. We need a higher yield stress in order to stabilize. When we dump it, it's stable. If we have low yield stress, it just run away. But at the same time, we need to have less stickiness. But it's very quite often that when after we dewater, the cake will become very sticky. And when you load it on a truck, you unload it, and then it will stick onto the truck, and it takes a lot of time to clean up the truck, and it's delayed a lot. So now, it's not just only the yield stress, but also the stickiness of the material is very, very important. So how can we quantify that stickiness? So we borrow a method from, we call it the pull-out method. Very common in the food engineering. So very much, we have a layer of the cold tailing, the water cold tailing in the middle, and here is two substrate that we want to normally steal. And then we try to pull it up until it's break. And then we record the force versus the distance, and we will get this typical curve of the pull-out test. So there are two parameters in here. The first one is the peak force or the maximum force. And the second one is the surface the area under the curve. We call it the tech energy. So these two parameters can be used to tell how sticky a material. So we use that method. So you will see that the pulling force is very different for two different cold tailing sample. So the first one is 5%. We have 5% swelling clay, and the second one is 10% swelling clay. And we see that the pulling force or the peak force is very different. So it is just one set of data. So we see without chemical, when we measure the yield stress of the cold tailing, and it strongly depends on the moisture content of that tailing. And it's go up, the yield stress go up very fast, exponentially, very fast when we have around that's 35% moisture content. And again, different cold sample will give a different yield stress. So these two are we haven't asked any chemical yet. So here, basically, if the higher yield stress is better. So you will see that increased yield stress. When you dump the material, it just can't stand by itself. But if lower yield stress, it will run away. So the same amount of material. And we did a lot of, we test with a lot of chemical reagent available on the market, 50 or something or more chemical. And we came up with very quite complicated, but very much the key takeaway message from here is when you ask polymer flocculant for sample, very much it will help increase the use stress of the cake. Cake here, the water cake, the water tailing. So it will help increase the use stress of the cake. However, at the same time, when we take all the parameter for the stickiness of the material, we will see that it's complicated. Some case it will increase the stickiness, some will decrease the stickiness, and very much we have no choice. But before we use it, we need to carry out the test to see which one will have to reduce the stickiness and at the same time increase the use stress of the material after the watering. So take one example. In this green curve, you will see that this is the maximum use stress we can get with this kind of chemical. However, when we look at here, it's in the middle of the D2 curve rather than on the top like this. So it's not a straightforward conclusion from it. And from if we take do experiment, so Ngoc he took some picture and we can see that very diverse range of stickiness of the material. Sometimes wet and sticky, sometimes dry and sticky, sometimes dry not sticky, sometimes wet with not sticky. It's complicated. But you we should publish a paper on environmental management something. So if you need one more detail, welcome to read that one. But again, the tech message here is, in order to dealing with the stickiness of the material, we need to bring in the knowledge from the food and engineering, another discipline. Okay, so now we move to the second case study. So where I try to upcycling alkaline mineral waste with a geopolymer application. So before we go to that second case study, the question is dry stacking the solution for my waste problem? Yes. We talked a lot about the watering and dry stacking, and they say, oh, we dry stack it, it's good. But actually, the question is whether that's good. That's the ultimate solution, yes. So here, if we look at the tailing, we have residual mineral, and inside we have water, around 60–70% water in here, some chemical. And if we have the watering, dry stacking, yes, water remove most of them. Some chemical remove, but the residual mineral is still there. And what happens if we have rain? Climate change, we have torrential rains. Water come back easily. So the watering, dry stacking is not the end of the journey. We need to keep moving. And for example, after dry stacking, and someday we find another method that can help recover some value mineral in the weight here, in an economic weight, and then we can further process it, and then we come up with another secondary tailing, and then we can dewatering, and we can dry stack it. It's still there. Problem of my way is still there. So for my thinking is, after the watering, we need to do one step further. It's called solidification or stabilisation. And then we deal directly with the residual mineral here. And in order to do that, we need to learn from the nature. We need to borrow a lot of knowledge from the rock cycle. So if we have knowledge from rock cycle, we can apply to the residual mineral here, and we can solidify the tailing. and we can turn it into different structure, more stable structure where water cannot penetrate, cannot reabsorb. But the question is, what kind of binder should we use? And with the right binder, we can convert tailing at a finely ground residue from ore extraction into different degree of aggregation. So rock here is mean different degree of aggregation. Rock, it doesn't mean that a very big rock. It can be soil. Soil also a rock. Soil is small rock. Or we can even make a bigger rock, artificial rock, from the tailing. So okay, so one question, you may know that water is most used material on us. You know what it comes second? Sorry again. Sand. Concrete. So it come to my surprise as well. So concrete is the second most used, widely used substance in the planet, just after water. Civilization, human being civilization, you see, we see building everywhere, concrete everywhere. And the problem with this, in order to have concrete, we need to have cement. In order to produce cement, we need to calcite limestone. And that's chemical reaction. Limestone, you calcite limestone in a heat, you get cement here, and you have to release CO2. And the cement production is very energy intensive. Grinding limestone into a small particle. Grinding causes a loss of energy, that's release CO2. Calcite limestone at very high temperature, 800 degrees, that generates CO2 as well. So, and as all of these CO2 together, the cement industry alone take responsibility for more than around 5 to 8% of the global CO2 emission. That's a lot. So there are lots of effort to try to find what is the alternative to cement. What is other material with a lower carbon footprint that we can use instead of using cement. And there are a lot of material, but geopolymer or inorganic polymer is one of the emerging as one of the potential candidates for alternative cement. And the term geopolymer here, or inorganic polymer here, is have a reason to come up with that name, but it sometimes is quite confused. And the concept, geopolymer can be used as an alternative because it have lower carbon footprint compared to cement. That's the first option. But the second thing that makes geopolymer interesting material is because a lot of kind of mineral waste or industrial waste can be used as a precursor to produce geopolymer. So it means the cost, it not just reduce the cost of geopolymer production, but also it can help solve the weight problem, mineral weight problem as well. So here, but in order to become a material to become a precursor of geopolymer, it had to be aluminum silicate rich material. It had to be have a lot of aluminum silicate content in that material. So here a kaolin clay, coal ash, when we burn coal ash, or bottom ash, bauxite residue as well. So these three are good candidates for to make geopolymer. So very much in order to make geopolymer, we have this material, and then we need to do alkaline hydrolysis reactions with the sodium silicate solutions. And when we put this material into the solution, this will start to dissolve the aluminum silicate component into different small fraction tetrahedral of silica and aluminum. So we call it monomer. And when we have the right ratio of those monomer, and a right concentration of the monomers, it will start to have polycondensation. And the polycondensation will form a extensive 3D network of aluminosilicate. And normally, this material can have some, this sodium silicate solution can have some additive effect as well. So it has silica supplement to help balancing the to reach the ratio, the right ratio of aluminosilicate. And also it will provide some charge balance for this structure. But very much the definition of geopolymerization is alkaline hydrolysis and then polycondensation. And the good thing is it happens at low temperature, relatively low temperature. So but very often that we carry out the reaction at ambient room temperature. But if you want to make it faster, around 70 or 80 degrees, that's enough, more than enough. So geopolymer is an exothermic polycondensation reaction. That is simple definition, but it's very painful to learn. It took me a lot of time, play around, and make material, lots of them, and I think that is geopolymer. But actually not geopolymer. It's something else. Until I see this one. So you see this is the same experiment condition, same curing, same temperature, just adjust the ratio a little bit different between the four, and you see that in this one, it generates a lot of heat, a lot of heat compared to this one and this one. And you see that the heat enough to swollen the plastic bottle I have. So that's the exothermic. And the polycondensation reaction will release water. This is the water. You see the water inside? So that's it. That two sides just tell me that, yes, I got geopolymer. So it's simple, but very painful to learn for me. Another thing is, so if you want to draw the boundary between the geopolymer and zeolite, and even ceramic somewhere up here. So geopolymer is very much at very low temperature, normally below 100 degrees. And the water to solid ratios is very low. If you want to make zeolite, you need to have water to solid ratio higher, much higher. And then the reaction temperature is higher than 100, normally higher than 100. So that's the boundary between the difference between geopolymer and zeolite. And ceramics, you know, ceramics even higher temperature. So I make a different kind of geopolymer from different material, different type, my weight. And the good thing is geopolymer, you can cutting it into different shapes, whatever shape you want to cut it. It's okay, and it will set very quick. So I just play around, have fun, cut into different shape here. And when you look at this symbol in a SEM, you will see that these are the undissolved particle of the raw material. And this undissolved particle is cemented by a material, and this is a geopolymer. And that geopolymer, if you take the chemical compositions, you will see the purple contour plots is the distribution of my data. I took a lot of data around this sample. I put them here, and there's a density plot. And you will see that the experimental data fit quite around these three are the theoretical ratios of the geopolymer. And the data is still around there. But one important thing is the chemical composition of geopolymer is very, very close to the sodalite with a counterpart, zeolite counterpart of geopolymer. So in order to understand the chemistry, the structure of geopolymer, actually I had to take a lot of knowledge from zeolite, from cement, and from ceramic, in order to just to understand how to make geopolymer from a mine waste. And then one step further, so I can build atomic scale structure of geopolymer by MD simulations. And then we can extract some information that can compare with the experiment. So I can predict how strong in the material by that MD simulations, by stretch the material after have it, stretch it, see what is the stretch strain curve look like. So that's the very much for fundamental of geopolymer, but here is one of the application. So I have 3 years on my Advanced Queensland project, working on this project. So I try to convert the fly ash and the bauxite residues. So they are the two locally available waste stream that we can use. So they are at one place, and now we can use and make something useful. So we can combine fly coal ash and residue and bauxite residue together to form geopolymer, and that geopolymer can be used for different applications. So we call it environmental application. And at the moment, we refer to have this at the on-site construction. So we use the local material, make it there, and use it there. So you may ask why we need to combine fly ash and bauxite residues. So this is actually the good combinations because the material, if you look at the XRD, QXRD, you will see that both material have a quite significant amount of amorphous material and aluminosilicate amorphous material. So they are good candidate for as a precursor for geopolymer. However, when we put it the coal ash and bauxite residue into alkaline solution, see how it dissolved. Because remember, before it has body condensation, it needs to dissolve first. These amorphous aluminosilicate have to be dissolved into monomer. So we want to see, so this is for bauxite residues, and this is for fly ash, and you will see that we need around silicate aluminum 1:1. That's a good ratio. And this one is below, this one above, and a combination of two would be a perfect mixture. Okay, so one of the challenges, geopolymer is very strict in terms of composition. The formula is very, very hard to adjust. You will see that I saw a picture before, just a small change in a formula, you will get a geopolymer. If it's very slightly changed, you will not get it. And here, when I put bauxite residue around the world, the chemical composition into this plot, you will see how diverse it is chemical composition. So it means we don't have any one solution for all, but for each mine site, we need to do the test before we do a bigger scale. So that is one of the challenges. And give you a sense of how strong in the material. So this is, so it can reach around 40, 50 megapascal. So that's quite strong. Comparable to the concrete, we have normal concrete. But the good thing is, it's very stable, chemically stable. It's not just mechanically stable, but it's chemically stable. So it's allowed to use for different applications, and we can apply it for different kind of mineral waste, different kind of tailing. So that's geopolymer very much for alkaline material, the bauxite residues. We can use that geopolymer to encapsulate acidic waste as well, so like copper lead zinc. However, in our group, we have another for sulfur tailing. We have another way, so we can utilize the precipitation of secondary mineral. So sulfur tailing weathering, it will be dissolved, and when it precipitate, we can utilize that precipitation at a cement fate. So that can change, you will see that. So this is the original pyrite particle, and when it changes, it will very much, when it forms secondary fate, it will change everything together into, and sometimes if you have a dry conditions, you can get a massive layer, very strong layer, and we call it half pan. So in our group, we determine the chemical composition of that layer, and then we even use microXCT to see what is the pore distribution and pore connection within that structure. And you will see that the pore connection is really poor. And because that this material can be a very good barrier for oxygen, not just water, but oxygen. Okay, so that's it. We go to the third one. So very much this is in the context of biomining, but not directly to biomining. It's a predecessor some of my work in this domain. So this one, if you go from my journey, it just reflect my journey from the bacteria to a peptide design. So I involved in this interesting project around 10 years ago, working with Michelle. So Michelle, a very good biologist, and she has very good AFM skill. So in this study, we use atomic force microscopy or AFM to see the different interaction forces between sulfur oxidizer and iron oxidizer with different mineral surface. So those two, sulfur oxidizer and iron oxidizer, are very AT and AF are very common commonly used in the bioleaching industry. In this study, we're very focused on the fundamental, see what is interaction force between the bacteria and the mineral surface. So the technique we use is we call it colloidal probe. So very much it's like you stick, you glue a small particle on the tip of your finger, and then you coat a layer of bacteria on top on that sphere and on that particle, and then you just move around that particle on the substrate to measure the force. So this is very typical force curve when we have bacteria with the charcoal pyrite surface, and you will see that the approaching curve, when we approach the surface, it will compress the layer, the bacterial layer. Not many different between the two here, the rest one. But the interesting information can be observed when you retract it. So you approach the surface, you leave it there, and then you start retract. So when you start to retract, because it's already contact and it forms some connection on the surface, interaction on the surface, now you retract. If you try to resist it, and the way it retract will be very interesting, because for this one, AT, you will see this, you can see a sawtooth pattern, but in here you have a stair-step separation pattern. It's very different. Okay, so another interesting finding from this project is the food that we supply to the bacteria. It plays an important role on the interaction force as well. So for example, in here, we have AF cell culture with either ferrous sulfide or elemental sulfur at key energy source. We use the same FM colloidal probe and measure the forces, and you will see, if we compare for silica particle, the interaction force between AF and silica particle. So this one is with ferrous sulfide, this one with elements of sulfur, and you will see again, this one we have a stair step, and this one is sawtooth. And The magnitude of the force is different as well. So pay attention on the scale here is 70, and this one just 25. So the same bacteria, we culture and we supply different food, and the interaction will be different. And then come to the state that we need to do some modeling, and in order to understand those results, we need to borrow knowledge from the civil engineering for nano indentation. But the message here is, at that time, I myself recognize the importance of the protein or the extra EPS or extracellular polymerase substances outside bacterial cell. That's also play important on for the interaction between bacteria and the mineral surface. So this comes to my work with peptide. So peptide, by definition, is a small protein made of amino acid. And those amino acids are linked by peptide bond. So this is the peptide bond. So we see that we have 21 proteinogenic amino acid. And that's 21 amino acid can be divided into 8 hydrophobic amino acid. The rest of them are hydrophilus. And for the hydrophilus one, we can divide into a charged and uncharged. And they are some special. So why peptide base reagents are good for mineral processing? So my point of view, so we have a very diverse, we have 21 options to select from. And very much, you can combine in any sequence you want. You take any of them, you combine in any sequence you want. And in any length you want. So that's give a very wide library of peptide. And then it have all the components. We have hydrophobic, and we have hydrophilus, and we have charged, we have uncharged. That is very much what we need for flotation. And it can provide multiple arms to reach the target. Because now the peptide can change in terms of its length. So it means if you find a very good arm, you can have a loss of that arm onto the backbone of the peptide. So it means now you have multiple arms to reach the target, not just one. The third one is provide selectivity. So the selectivity here is not just from the chemical selectivity, but also it's come from the steric hindrance. So I will show you in the next slide. So when you put into a polymer chain, a peptide, it will moving around trying to find the minimum energy configuration. And if it finds a minimum configuration, it will very much stick to that one. And so it means alongside with the chemical selectivity, you also have the structure constraint or steric effect as well. They're very strong. And so don't remember that's a ring reagent. That makes it good. Okay, so here it's come pros and cons. Those are pros and now cons. So we have a very diverse library of peptide we can try, but we need to understand the level of complexity of peptide. So peptide, we will divide into primary structure. So that's just the second amino acid sequence. And then you have secondary structure. So this is one example of, I have F6 and AL6 and F6. So very much F6 is this one, but I try to put more of hydrophobic amino acid into the backbone. So you see on the color here, it's just, this is hydrophilic, this one F is hydrophobic. When I put more hydrophobic in, it will change the secondary structure. So you see. And that, not just the secondary structure, but when you put them in together in a solution, they find together, they aggregate together and form a ternary structure. So you see this one is from fibro, many peptide. This peptide, put them So 16 or something in here, and it's assembly into this fibro. But this one is have a fibro, but more branch fibro. So with this, I have some interesting project with Professor Longbin Lecoq and Noni and Amin, our PhD student. Interesting domain because we try to develop bio-inspired conducting peptide, nanowire. So very much we inspired by geobacteria, and some of the EBS can be used for transport electron over great distance. So that's why we need to study from this, and we have a de novo design from new peptide, and we come up with a lot of peptide, and MD simulation can very much confirm the AFM result. So now I guess the more interesting part and more related slide to you. So this is some of the simulations that I did for peptide interact with silver. So that can be used at peptide-based flotation reagent for silver. So this one you see it a slab of silver metal, and then on top you see 6 different peptide, and we see that when you put them together, peptide will try to arrange onto the surface, absorb onto the surface. And this one is for a nanoparticle, silver nanoparticle, 3 nanometer. Okay, so for another work I'm doing at the moment is very much on the rare element recovery from waste stream. So lanthanide, when you have formula leachate, it's in iron, and because you have a very small difference in terms of radius, iron radius, it's only 3+, iron 3+, but the and the radius of the lanthanide ion is very, very similar together. So that's why it's really hard to separate. And bio-based material is one of the good options to recover different rare elements from the solution. So it's interesting that the field is quite, I'm not saying it's new, but I mean it's still not a lot of significant development in terms of material development material. So for example, they still use this called EF hand calcium binding loop. So this one is you have a F helix, and then you have a curve, and then you have another helix, and then you have a lot of oxygen. So this around this green domain is offer a lot of oxygen that can coordinate with the calcium. So that's happened in nature. So it's very much EF hand is like this. So you have one helix here, and a curve here. You have a lot of oxygen around here, and calcium can come in here and then sit perfectly in this domain. So that is for calcium 2+, but lanthanide iron is 3+, but still work. So this is one of my simulation, recent simulation. So I come with this modify the same EF hand motif. So we call this lanthanide binding tag. And you will see that this is a lanthanium. And this domain is the one, the green you can see here. And this is quite quite stable. So that is some interesting domain that we can use. So that's very much sorry, one last thing. So early this year, we just published a review paper on this biomining. Just list a different option for biomining in there. And if you interested, so please have a look. Okay, so we go back to the very first question. Can you help me to tell me how many disciplines are involved during my talk? Sorry, I'm not want to show my research, but I mean it's just that the nature of the work. We had to deal with it. Can you tell how many? That's very good answer. And very easy answer, multi, right? So that's it. Come back to my title, my talk, multidisciplinary. We have more than one for sure. But the question I would like to give back to you, and maybe we have to work more, whether we want to keep that multiple disciplinary approaches to solve the problem, or we want it a single integrated discipline to solve the problem. Which one is more efficient? So that is very much an open question, and very much what we want to do for the next, for make a better solution for my weight. Thank you very much.
Thank you very much, Tuan. It's really interesting work you're busy with. Do we have a question for Tuan? Tuan, maybe from my side, when you talked about the geopolymers and producing them as a substitute for cement, do you have an idea of the improvement in terms of carbon footprint, on how much better that would be in terms of conventional cement production?
Yes, we do have a lot of study on that to compare the CO2 equivalent or CO2 footprint between cement and geopolymer. A lot of work available on literature, but I can say it's because most of the geopolymer at the moment are from fly ash. And remember, in order to get fly ash, we need to burn coal. So someone if say, oh, it's very green material, very low carbon footprint, but they just ignore the fact that in order to get fly ash, you need to burn coal. So that is CO2 category 3. So they're counting for category 1 and category 2, but they forgot, or they ignore category 3.
Yeah.
But I mean, overall, if you still counting for that category 3 CO2 equivalent, geopolymer is still lower. I would say around 60% lower than the cement. Oh. But again, this material is not just lower CO2 footprint, but geopolymer is very chemically stable compared to cement. So remember, cement, the definition of cement is calcium hydrate. So it means calcium absorbs water. So it means if you have applied high temperature or you have chemical in it, water will go, and it go back to just calcium, not calcium hydrate anymore. And your whole structure collapse. That is your structure collapse. But geopolymer is chemically linked aluminosilicate network. So I spent like last 5 years, did a lot of tests in different stability, biostability, chemical stability of geopolymer in different environments. But because I cannot share here because it's with some limits in industry, so I cannot share, but it's very, very stable compared to cement. Yep.
Okay, maybe one last question since we've run out of time. Online, there's a question from Michael. Great presentation covering a broad range of approaches. I have a number of questions from an asset closure perspective, but as an initial question, with regard to non-natural polymers and naturally some of the geopolymers, how much work have been done to understand the long-term degradation products and potential effects on water quality?
So it's a good question. So in terms of the test of time for geopolymer is still uncertain. So some people, I mean, a lot of people, they believe that Roman concrete kind of geopolymer, or Greek pyramid, it also kind of geopolymer. We still have a lot of argument on it, but I mean, Roman concrete or pyramid stand the test of time. So that's indirectly answer the question that geopolymer will stable over time. in terms of water, its effect on the water quality or something?
Yeah.
Yes.
Yeah, water quality.
Yeah. So if we apply this geopolymer in aqueous environment, so I'm not quite sure that's the context you want to ask, but it depends on what kind of environment. If you apply geopolymer in a sunlight, water, or seawater, it will strengthen the material. So I did quite many tests with seawater, incubate geopolymer in seawater. So it's helped to strengthen the material. So that's it. When you apply that into seawater environment, that will be stronger. If you put that into a leaching test with a normal water, some excess amount of sodium will come out because remember, in order for the geopolymer happen, we need to have a hydrolysis reaction, and that hydrolysis reaction we need to use high sodium hydroxide concentration, and normally we use more than enough to help to accelerate the dissolution of the material. So because we use more than enough of sodium, so when the whole structure becomes solid, though excess amount of sodium will loosely bound to the structure. So if we have a method to wash away those excess amount of sodium, and then after that we can use separately. So remember, inside the structure we call it structure sodium. It's similar to soda lime. So inside the cake, because alumino tetrahedral, it negatively charged, so it needs to be balanced by sodium. And if that 1-to-1, I mean sodium ion to aluminum 1-to-1, it will be stable because that the stick there, it balance the charge, it stick there stable. But what I mentioned before, it is the sodium that not stick to aluminum side. We need to wash it away before we use it.
Okay. Thank you very much, Tuan. Apologies for the online questions. That's all time we have for today. Feel free to reach out to Tuan afterwards. We will put his email address on the chat if that's fine with you. Okay. Thank you, everyone. Let's say thanks to Tuan again for his presentation. So next week we have Oscar Castro from FL Smith talking about digital twins for SAG optimization. So I hope to see you all there. Thanks.